Welcome to another Physics 2 on-ramps demonstration presentation. Today, we're going to talk about Faraday's law, the basis of many aspects of our technology. And it depends on the definition of magnetic flux. Magnetic flux is just a measure of how much magnetic field is crossing perpendicular to a surface. And so it depends on the field and the area and the angle between the field and the normal to that surface. So however much flux is crossing a surface will determine its action under Faraday's law. Faraday's law says that the electromotive force, remember the EMF or electromotive force is actually not a force, but it's a voltage. And that voltage is induced around some path, and we get a voltage induced around a path whenever we change the magnetic flux through the area encircled by that path. So Faraday's law is very simple. It says this voltage is exactly equal to the number of loops we might wind around that path, because we get a voltage around each loop, times the change in flux with time, the rate of change of flux with time. So this station we'll be using this half today, and it has a strong magnetic field. These are the pole faces of a permanent magnet. And it has a meter and nothing else really. Just connected to that meter are some wires, for example, these loops. And as Faraday's law predicts, if we change the magnetic field through these loops, we'll induce a voltage around them. So let's try that. I'm going to take these loops, keep an eye on the meter, and watch what happens as I increase the flux through the loop. There's an increase. We saw a positive deflection. Now I'm going to decrease the flux through the loop by pulling it back out. Decrease, there's a negative voltage induced. So the sense of the voltage that's induced one way or the other way depends on whether we're increasing or decreasing the flux. Another example is a coil. Here's a coil that's just hooked up to that same meter. And if we change the flux through it, we'll see an induced voltage. So I'll take a permanent magnet and insert it. And as it's changing, while it's changing, we see that induced voltage. But notice, I'm holding it still. When you're holding it still, there's no induced voltage. You need a change in the magnetic field, not just a magnetic field. Now I'll pull the field out and decrease it, and then once again you see the opposite sign. As we decrease the field, the voltage goes the other way.